Afternoon, everyone. Yes, my name is JP Mosen, and it's certainly a pleasure to be with you today. And my colleagues and I will be with you the next 12 weeks or possibly 13 weeks if you are participating in the depth sessions. Uh, we will be walking you through the material that we feel is very important and has a high probability of appearing in the morning part of the exam. The 12-part series is designed to prepare you for the breadth part of the exam, and that is what we will do. Today, I will cover structural analysis with you, and the topics that we cover in this session and others follow the topics that are explicitly listed in the NCEES series of topics that are covered on the exam. Once again, we concentrate on the topics that we feel have the high probability of showing up on the exam. As far as structural analysis is concerned, you need to remember, and all of you at some point have had a course in structural analysis, and you do remember that there are two types of structures. One is determinate, the other is indeterminate. There used to be, the PE exam, it used to cover both determinate and indeterminate structures in the morning exam. However, several years ago, about 3 years ago, when the construction module was added to the test, they eliminated, for the morning exam, they eliminated the indeterminate structures analysis. Therefore, I will tell you, those of you who are taking in the afternoon, if you're taking something other than structures, all you need to be concerned about is indeed the determinate analysis, and we will talk about that, just the determinate analysis throughout this presentation. However, you do need to know how to distinguish between a determinate structure and an indeterminate structure, and that I will show you how to do. All right, on the test, they may ask you, give you a structure and ask you if it's determinate or indeterminate. That you need to know. However, please pay very close attention. Those of you who are planning on taking the structures exam in the afternoon, you, however, are responsible to know how to analyze indeterminate structures. All right, just those of you who are taking structures in the afternoon. For that reason, towards the end of this presentation, I have the topic called moment distribution. Moment distribution, for those of you who are structural engineers, you recognize the terminology, and that is a technique that helps you quickly analyze an indeterminate structure. I have a series of problems that deals with that in this document, in the handout, but please pay very close attention. I do not intend to cover that part of the presentation today. I will not do that. It's just there for your reference. And indeterminate structures analysis will not be covered in the structures depth. So this is where you get that information. All right. The rest of you who are taking in the afternoon something other than the structures focus, let's work on learning how to analyze determinate structures. But before we do that, who can tell me yeah, Matthew is asking a question. I answered that. Indeterminate analysis is not required for the general portion. Matthew is saying general option in the afternoon. I'm not aware of a general option in the afternoon. We're talking about the PE exam here. Okay, so let's continue. How do we tell whether a structure is determinate or indeterminate? So here we have examples of indeterminate. I'm sorry, these are determinate structures. Let's start with the top beam. That's a beam. And tell me, who can tell me, how do we decide? How do we decide whether a structure is determinate or indeterminate? Who can tell me? If you could just type it in just very quickly, and then we'll go from there. How can we tell whether a structure is determinate? Okay. Okay, Amanda is saying number of unknowns versus number of equations. That's correct. And Tyler also says the same thing, number of variables versus number of equations. Okay, very good. Let's talk about that. So the question is, how would you be able to tell whether a given structure is determinate or indeterminate? Well, this is what you need to do. Tyler is correct, and so is Amanda, and several other ones mentioned the same thing. Arash also has a suggestion. So here's what you guys have to do. Let's say that this is on the test, and we are looking at deciding whether this is a determinate or indeterminate. Step number one, the first thing that you do is you need to identify the supports. All right, so how many supports does this structure have? The beam. All right, well, I'm going to show you the supports. This is one. This is a support. What type of support is that? That is a pin support, P-I-N. That's a pin support. And how many unknowns are there at a pin support? When we talk about unknowns, please write it down. We're talking about the number of reactions. So how many reactions do you expect at a pin support? Those of you who said 2, you are indeed correct. All right? So 2 reactions we expect at a pin support. Now, what about the other support? We have another support that's right over here. Right over here. And guys, that is a roller. Whenever you see a circle sitting on a surface, that is a roller. And how many unknowns are there at a roller? 1 reaction. Jacqueline Old says roller has 1 reaction. That's correct. All right. Now, how many other reactions do we have here? Well, first, let's look at how many unknowns we have. And this is another support. That's another support that we have. Now, this support, what kind of support is this? You're right, that's a roller. So how many are the total reactions that we have? How many total unknowns? The total reactions. So we have 2 at the pin support, 1 and 1. So there are 4. We are 4 unknowns. How many equations of equilibrium do we have to use? Well, the number of equations of equilibrium, there are 3. There are always 3. All right? So here's what you need to do. You need to compare the number of unknowns with the number of equations that we have available to solve those unknowns with. So we had 4 unknowns and 3 equations of equilibrium. Here's the problem, however. If the number of unknowns equals the number of equations, that makes it a statically determinate structure. However, with this particular beam, and this is very, very important, I want all of you to please pay attention. With this particular beam, there is a condition that I have to highlight for you, and that is simply this this hinge. You see that? Does everybody see that? That's called an internal hinge. And usually they either use the word hinge or they use a circle within the beam, as you can see there. Now, what happens with an internal hinge is that the internal hinge gives us one additional equation of equilibrium. Write that down. An internal hinge gives us one additional equation of equilibrium. And this is something that they can and they will do on the test, all right? So Matthew is asking, what do you mean by number of equations? We're talking about the equations of equilibrium, which are three of them, Matthew. One is summation of forces in the x direction equals to 0, summation of forces in the y direction equals to 0, and summation of moments is equal to 0. Those are the equations, Matthew. So in this case, however, we have four unknowns. However, because of this internal hinge, we have the three original equations of equilibrium and then one additional one because of the internal hinge. Therefore, we have four unknowns and four equations of equilibrium. Therefore, this particular beam is indeed statically determinate. All right, let's look at the truss. This is a truss structure in the bottom. I'll wait for you. Tell me, how many unknowns do you see? Well, again, what you have to do, all you have to do is identify the supports. We have one support here. That's a pin support. That gives you two unknowns. And then here's another roller support. So that's all the supports that I see. So those two supports will give you three unknowns. And again, Matthew, how many equations of equilibrium do we have here for this truss? Since there are no internal hinges, we only have three equations of equilibrium. Therefore, three unknowns, three equations of equilibrium, that makes that structure determinate. All right, let's move on to the next slide. Here, there are examples of indeterminate structures. So please help me out. If we look at this, Mary Hill is asking me, what is the condition at the hinge? That gives us a moment equation. So what we can do, Mary, is to write an equation of the moment around wherever the hinge is, and that would be equal to 0. All right? Very good. Excellent. So let's take a look at here. First, step number one. If we're looking at the top structure, which is actually, this is, if you pay attention, the left support is a fixed support. So how many supports do we have? Well, I'm going to see if I can circle them. This is a support, and that nomenclature shows a fixed support. And please remember, write it down. Every time we have a fixed support, there are three unknowns. Summation of, well, there is a reaction in the x direction, there is a reaction in the y direction, and since this is fixed, it does not allow the beam to rotate in any direction. Therefore, moment is also 0. So just remember, at a fixed support, there are three unknowns, three reactions. Then the next support that we encounter is this one, and this is indeed, that's supposed to be a circle, so that is a roller, so one unknown. And then the other support that I see is this one on the far right, and that's also a roller. And I already see Donald says 5 reactions, so is Van. Van, your last name is not easy to pronounce, so I'm just going to say Van if you don't mind. So we have 5 unknowns. All right, guys. The next thing that you see, take a look and see, are there any internal hinges? I do not see any internal hinges. All right. Then how many equations of equilibrium do we have? 3. All right. There you go. Ryan Allen says 3. By the way, hi, Ryan. So what we have here are, write it down, five unknowns, three equations of equilibrium. If the unknowns, the number of unknowns exceeds the number of equations, that is definitely an indeterminate structure. All right. So we have identified that as an indeterminate structure. But guys, if, by the way, I use the word guys a lot. So, and I refer to both genders by the word guys. So you will hear that a lot. So that's an indeterminate, but what you see here, uh, three equations of equilibrium, five unknowns. If they give you this question, what they will say, they will also say, possibly they will ask you, what is the degree of indeterminacy? What's the degree of indeterminacy? And I'll tell you, that simply is, this is how you calculate it. Subtract the number of equations from the number of unknowns. In this case, 5 minus 3. The degree of indeterminacy is 2. All right? Or another way of asking is it's indeterminate to the second degree. All right, very good, very good. Now, what about the frame? You will also see some frames on the exam. So here's the frame. Tell me, how many unknowns? Well, if you do that, if you identify, Helen, tell me how many unknowns, it would be, find the supports. This is a support. It's a fixed support, by the way. That's a fixed support. This is a fixed support. There are two fixed supports. Each have three unknowns. So many of you are saying 6. So 6 unknowns. And how many equations of equilibrium? Do you see any hinges? No. So the equations of equilibrium, 3. So we have 3 equations of equilibrium. So we have 3 equations of equilibrium and 6 unknowns. Definitely indeterminate. And to what degree? Third degree. 6 minus 3. Amgad Fahmi is saying that he didn't get the discussion about indeterminacy. Fahmi, just very quickly, I'll tell you, check the number of unknowns that you have against the number of equations that are available to you. If the number of unknowns, which are the reactions at the supports, if that exceeds the number of equations that you have available to you, that is indeterminate. All right? If you have further questions, Amgad, please send me an email. Let's move on, guys. All right. Let's talk about stability and determinacy of trusses. Trusses will be on the test. All right, you will see some truss problem on the test. And they may ask you whether it's a stable or determinate, mostly determinate, and I will give you this equation that I will share with you in just a second. But also, in terms of trusses, you will be responsible to analyze the truss, and by that we mean you have to be able to find the force in each member. For example, AB, that's a member. You need to be able to find the internal force in that member, and also you need to be able to decide whether that member is in tension or compression. The next few minutes I will show you exactly, I will show you the quickest ways to identify the internal force in a truss member. Also, I'll show you how to decide whether a member is in tension or compression. But before we do that, with your permission, I'm going to go over this equation that tells you whether whether a truss is stable or not. All right. Now, the equation. I'm trying to erase this thing. Cool. All right. Now let's go down here. The equation is simple. The left-hand side, 2J, is equal to M plus R. What I need for you to please note, what does J stand for? J is the number of joints. Number of joints. Now, in this trust, the point A, any point where the different members come together, point A, for example, that's a joint. B is a joint. C is a joint, and so on. All right? Then M. M in this equation, as you can see on the right-hand side, it's the number of members. So tell me, how many members do we have here? Just count the number of members. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I have 13. Mary Hill says 13. Those of you who are saying 13, that's correct. So we have 13 members. So M, lowercase m is 13. Now, what about R? R is the number of reactions. Number of reactions. Guys, these are the number of unknowns, number of reactions at the supports. So let's take a look. Where are the supports? One support is at A, and that's a pin support. Pin support has two reactions. And then at E, we have a roller support. There's one reaction. So the total number of reactions, lowercase r, would be what? 3. Okay, very good. So please help me out. The right-hand side of this equation, m plus r, is 13 plus 3. I get 16, all right? What about the left-hand side? Left-hand side is 2 times j. J is the number of joints. How many joints are there? Just count them. A, B, C, D, E, F, G, H. How many do you get? I think, yeah, John Taylor says 8. I agree. So j is 8. But you multiply that by 2. 2 times 8 is 16. So if 16, the right-hand side and the left-hand side, if they are equal, then the truss is determinate. In this case, the truss is determinate. That's all there is to it. Now, the truss would be indeterminate if 2 times j is less than m plus r. If the left-hand side is less than the right-hand side of this equation. And the truss would be unstable if 2j is greater than m plus r. All right. Now let me ask you. We have a lot more to do, but I want to ask you a question. Can you tell me, please, what is the significance of this equation? Why are we checking 2j times m plus r? Tell me what 2 times j represents. Who can tell me? This is critical thinking. Okay. And Stephen Marzi says sum of fy, fx at each point. Sum of... Yeah, that's correct. Absolutely. Stephen Marzi. Excellent. Excellent. Are you a structural engineer? Here, 2 times j, guys. Yeah, okay. 2 times j actually is, see, at each joint we have 2 equations of equilibrium. Because each joint, for example, C, D, B, whatever, whichever joint, we consider that to be a hinge. And certainly all we have to do is satisfy 2 equations. Summation of forces in the x direction equal to 0, summation of force in the y direction equals to 0. So as Stephen says, here's what happens. 2 times j, guys, is simply the total number of equations that are available to us. All right? 2 times j is the number of equations that are available to us to solve this truss. All right? That's the left-hand side. The right-hand side, m plus r, number of members. See, the internal force in each member is an unknown. And R, number of reactions, those are unknowns. So the right-hand side, m plus r, is the number of unknowns. The left-hand side are the total number of equations available to us. And just like what we did previous to this slide, if those numbers are equal, then it's determinate. If not, different. All right, let's move on. Guys, what I need for you to do is help me now to analyze this truss, and you will be able to to learn, next I want to show you how you can find the internal force in each trust member. And these kinds of problems show up on the test quite often. So in this case, we are looking at the trust that's in front of you, and then we want to know the force in members BH, BC, and DG. Now, we are also given the geometry of the truss. We know the dimension of the various members. So tell me something. What are the methods that you learned in school about analyzing a truss? There were two methods. Who could remember? Matthew, the answer to your question is no. No, it's always 2 times J. That goes back to each joint. Okay, Ian is telling me a method of joints and method of sections. Absolutely, he's correct. So there are 2 methods that you've learned in school to analyze a truss. So method of joints and method of sections. So I'm going to cover both of those. But here's what I'm going to do, guys. And I want you to be pay very close attention, because on the exam, you need to be able to identify the quickest method to solve each problem. All right? And that's what I'm interested in showing you. I want to show you in what situation do you decide the method of joints would be the best or the method of sections. All right? So I really need for you to pay very close attention and understand how to decide which one would be the quickest in a given situation. Now, and what the method of section is or the method of joint, we will go through both of those when I solve the next 2 or 3 problems. But here is what I will tell you. Please note, if you're, for example, solving for a member, let's say AB. This is, by the way, this is point A right here. The left point is A. So if you're looking at member AB, that's close to a support. If you're solving for that, I would recommend the method of joints, definitely. If you're solving for AH, I would recommend the method of joints. All right? Now, there's one other thing that I would tell you. If you are looking at a T section, and this is really important, guys. If you're looking at a T section. Now, this is a T section right here. Look at BH. You have member BH, and let me show this in red. Let me see if I can, yeah. You see this BH? That's a vertical member. And then you have AH moving all the way to HG. This I refer to as a H section, not, I'm sorry, a T section at the point H. All right? Where else would you see a T section? Well, here. DF is vertical to GE. And there's another one here. So write it down. If you're, for example, solving for a member such as BH, DF, or CG, if one of the ends, look at both ends of the member, and if one of the ends is a T section, definitely what you need to do is apply the method of joints at that T. All right? That makes things very easy for you. All right? So make a note of that. Now, if you're solving for a member that, let me go to the next slide. If you're solving for a member that is away from a joint, for example, this one, BC or CD, a member like that, away, sort of in the middle of the truss, I would recommend that you use the method of sections. All right. So these are guidelines. Which method would be the quickest for any given situation? Now, in this case, we are asked to find the force in member BH. All right, guys, I want everybody to solve this with me, please. This is BH. What did I tell you? That is a T section. That's a T section at H. What did I say? Well, you know, you need to apply the method of joints at the point H. By the way, please remember, um, Arash mentioned this in one of his comments. These members in the trust, there are two force members. What that means is the force can only act along the member. All right? These are all called two force members. So the forces they are along the member, which means what that means to you and me is to solve and find the force in member BH, you can analyze the joint B or H. You can isolate and analyze either of the joints at the ends of the same member. And if you do it correctly, you will get the same answer, no matter which end joint you analyze. All right? In this case, as I told you before, it's a T-section. Definitely apply the method of joints to point H. And what do we mean by that? Well, you isolate the joint H, and here's on slide 8, I'm showing that. You isolate the joint H and draw the free body diagram. Draw the free body diagram, and this is at the bottom. This is the free body diagram of joint H. What you have to do when you isolate it, guys, you cut the member. Cut the member here, here, and here. All right? And when you cut a member, guys, you make, in my opinion, what you do, you make the internal force become exposed. That's why when we cut HG, for example, I replace it with the internal force HG. Same thing with BH and the same thing with AH. All right? Now, that is the free body diagram for the joint H. Now, once you have the free body diagram, what you need to do is apply the equations of equilibrium. And as Stephen told us earlier, there are two equations of equilibrium at each joint. Those are summation of forces in the x direction and summation of forces in the y direction. Now pay attention. If you sum the forces in the x direction at the joint H, what do you get? You would get FHG is equal to FAH. What are you solving for? We're solving for FBH. All right? So the unknown would not even show up in the summation of forces in the x direction. However, if you sum the forces in the y direction, as we have done here, assuming y going to the top is positive, what do you get? FBH positive. Is there anything else in the y direction at the joint H? The answer is no. Therefore, FBH would have to be equal to 0. Several of you, including Donald, identified this and said earlier that FBH is 0. In fact, if you are able to recognize that by inspection, that's fine. But I just showed you so you can see. This is called a 0 member. All right? Some of you may ask, say, well, all right, if BH is, let's look at the truss up here. If BH, this member is a 0 member, which means it's not capable of resisting any loads or carrying any loads, well, then what happens to that 300-pound force that's acting in the vertical direction at B? Well, please pay attention. That 300-pound force will be reacted upon by the Y component of these inclined members, AB and BG. All right, let's move on. Next, I want you to help me find the force in member BC. Now, BC, remember, the first thing is I want you to take a look and decide which method should you use. Remember, Ian told us there are two methods, method of joints and method of sections. Here, BC is a member in the middle, and I would recommend we use the method of sections to analyze this. All right, very good. And Fahmy is saying method of sections. That's fine. Sandra is method of sections. Let's do it. When we use the method of sections, what is it that we do? Well, basically, we cut the truss at a given section. Here, that would be the section that I would use. In other words, I'm going to cut through BC, than the diagonal and the bottom chord. Um, let's take a look at the next slide. All right, so there it is. Please take a look at the top, and this is the section. It's a vertical section, so basically, since we are looking for the force in member BC, BC should be one of the members that we cut. All right, so there you go. That is the section that we do. So what do? First, we cut the truss. The next thing that we need to do is the following. We need to draw the free body diagram, the complete free body diagram, either to the right or to the left of the section. And that you could see down here, guys. You can see the free body diagram. In this case, I'm using the free body diagram to the right of the cut. It really doesn't matter whether you choose to use the one to the right of the cut or the left of the cut. If you do it correctly, you will find the right answers. However, there are a couple of things I need to tell you. In this case, since I'm using the segment of the truss to the right of the cut, there are a few things that you need to pay attention to. First of all, the members that you cut, you can't just go through life cutting truss members and just leave them hanging. Whenever you cut a member, the internal force in that member becomes exposed, as I told you before. So I cut BC, I'm showing the force in BC. All right? Which other ones did I cut? BG. All right? Look at what I did. I'm showing the internal force in BG as such. And then also HG, there it is. All right? Now, what about the external forces? Here, and this is very important, especially those of you who have not done many of these kinds of problems since you left college. What about the external loads? Well, the 400 pounds, for example, is acting at the point C. So here's what you need to do. Is the point C part of this free body diagram? And the answer is yes, it is. Then you will include that force. All right? Now, as opposed to, you see up here, it's pale. You don't really see it very well right now, but that says 300 pounds. There is a force of 300 pounds there. All right? So do we include that? Well, no, because that acts at the point B, and the point B is not part of this right-hand side of this truss. All right? So the 300-pound force at the point B we don't need to include that. All right. What do we do next? Well, remember, we want to find the force in member BC. So this is the unknown. What do we need to do? Who can tell me what's the easiest way to find the force in member BC? Who can tell me? Okay, Matthew, Andrew, Jonathan. Hold on. Ryan, Black and Veach. Several people are saying right the moment about the point G. Now, we have some other suggestions also, but please pay very close attention. If we write the moment about the point G, those of you who are saying writing the moment about the point G is the quickest way, you are correct. All right? So writing the moment about the point G is indeed correct. And if we write the moment about the point G and solve for the reaction at BC, that would be the quickest way to solve for that problem. Now, let me explain why. Because, in fact, that's what I did here. Look at the equation up here. I summed the moments about the point G, set it equal to 0. The reason that's the quickest way and the best way to solve this problem, guys, is because, look, how many unknowns do we have? Well, we have BC. This is unknown. The force in BG is unknown, so is HG. But if we write the moment about the point G, two of the unknowns disappear because BG and HG both go through the point G. Therefore, they will not show up in this equation moment about the point G. Therefore, look at it. That equation is just one equation, one unknown. Now, you also see RR. That's a reaction at the right support, and that I didn't show you, but you should be able to solve that independent of this. All right. So RR, even though I show it as an unknown, but that's a reaction at the support E that you should be able to do it by equilibrium. So reaction at R is or reaction at E is 275. Substitute that in there, and then we get this. The answer is what? The answer becomes 733. All right? Does everybody follow? You solve for FBC, and it comes out to be 733 pounds. Does everybody follow that or accept that the force in member BC is indeed 733 pounds? Now, there's one other thing here, and that is it says it's in compression. Now, how do we decide whether it's compression or tension? Remember I told you earlier that you also need to learn how to decide whether a force is in or a member is in tension or in compression. Brian, in order to find this 275 pounds, Brian is asking, how do I get the 275 pounds? For this truss, this is what you need to do. Please write the equations of equilibrium about the point A. Sum the moments about the point A, and the only unknown would be RR, and you get 275. Do me a favor, Brian. Do that and see if you have any problems with that. Please send me an email, and I'll be able to do that. All right. Fami asked why RR has negative. I think what you're talking about is this here. Why is that negative? That's the direction. That's the direction, because you see, Fami, we are assuming that clockwise is positive, all right, and that RR about the point G in the direction that is shown will cause a counterclockwise moment. That's why it's negative, all right? Again, if you have any questions with that, please let me know by email. But this is important, guys. I need to cover this before we move on. How do we decide the force in member BC is in compression and not tension? All right? Here's what we do. In order to do that, you have to decide whether the internal force in the member, let's talk about BC. The internal force in the member, if the force pulls away from the joint, pay attention. If the internal force pulls away from the joint, that member is in tension. All right? Now, if the internal force pushes towards the joint, then the member would be in compression. All right? Now, when we analyze these members, for example, BC, we don't really know whether the internal force is pushing towards the joint or pulling. What we do, we make an assumption. And if you recall, when I told you to use the method of sections and use these three forces, BC, BG, and HG, what is my assumption here? I assume you have to make an assumption towards about the direction of the internal force. I have assumed all three to be pulling away from the joint. Does everybody see that? Just look at the arrowhead. All right? So in other words, I've assumed all of these three are in tension. All right? Now, when I analyze the beam, now pay attention, the answer that I received, 733 pounds, has a negative. Do you see that? That carries a negative. That came out to be a negative 733. That negative, this is very important, the negative simply um, says that the initial assumption regarding the direction of the force was not correct. And even though I assumed FBC to be pulling away from the joint, but the answer comes out to be negative, that negative says, no, no, this is not pulling away from the joint, it's the opposite. And that's why my analysis tells me it's not pulling away from the joint, it's indeed pushing towards the joint. That makes it in compression. That's how you decide whether it's in tension or compression. All right? Now, before we move on to the next slide, I need for you to help me with something. If I ask you to please find the answer to, find the force in member HG, how would you solve it? I want you to help me find the force in HG. Tell me what is your recommendation. Well, we would use the method of sections, and in fact, I will use the same section, and I would use the same free body diagram. So Matthew and Ian are making suggestions. They're telling me in order to find the force in HG, the quickest way to do it would be to write the moment about the point B. And that indeed is correct, guys. I want you to pay attention. If we're looking for the force in HG, this bottom member, and you choose to use the method of sections, and you use this free body diagram that I'm showing you, the quickest way would be to write the moment about the point B. All right? What you need to do, sum the moments about the point B, and why that's so helpful is because it will eliminate both BC and BG, because they both go through the point B. All right? So we will eliminate those two forces. The only force that remains in the equation would be the force in HG, which is the unknown. So one equation, one unknown. Now the question may arise that you may ask me, can we write the moment about the point B? Because B is not part of this free body diagram. Well, B is not part of this free body diagram, but you know, for equilibrium, for this truss, this portion of the truss that we are using as free body diagram, for that to be in equilibrium and stable, it should, the moment about any point on the, let's say this screen, that plane of the screen, the moment would have to be equal to 0. B certainly satisfies that. So yes, you can sum the moments about the point B, and you will have that HG. Do it on your own. Do it on your own. See if you can get it. Now let's move on to member DG. Next, I want you to help me, please, find the force in member DG, which is that diagonal. Which method would you use? Sections or method of joints? Method of sections would be the ideal one. And in this case, I'm showing you the section that I've chosen. You cut through CD, GD, and GF. All right? The free body diagram is at the bottom. Do you agree with that? You should, because it is correct. And so that's the free body diagram. In this case, I chose the the section to the right of the cut. Now, I want everybody to pay attention. How would you do this? Helen, what would, in your opinion, what is what would be the best way to solve for the force in DG? There are several ways of doing it. I'm interested in sharing with you the quickest, the most direct. All right? Paul is saying sum the forces in the y direction, and Paul is indeed correct. Paul is saying the quickest way to solve for the force in DG, which is that diagonal, would be to sum the forces in the y direction. Helen says moment about the point F. Well, yes, that is possible, but the problem with that is that there will be two unknowns in that equation. Look at it. The force in CD would cause a moment about the point F. So will the force in DG. All right? So even though that's correct, but it will be multi-step solution. However, if we go with Paul's suggestion of summing the forces in the y direction, then what happens is that we will only have one equation, because how many unknowns do we have in the y direction? Only two. Only two. Because one, you got it. One is the y component of the force in DG, and the only other force in the y direction is this reaction at E, RR. Nothing else. You may ask, what about the force in FD? All right, think about it. What about the force in FD? That would have a vertical force. Well, yes, but have we cut that? We have not. As long as a member stays intact, the force in that member does not become exposed, and we don't have to worry about it. You can also say the same thing about DE. DE has a force in the y direction. But once again, have we cut that? No. So as long as it stays intact, we don't have to worry about that. All right. So the most direct is summing the forces in the y direction. In fact, on page 13, I'm showing that. Sum the forces in the y direction for the entire free body diagram for this entire section. All right. And as you can see, RR is equal to minus DGY. That's equal to 0. All right? So then DGY would be equal to 275 pounds. Pay very close attention here. DGY, that's the Y component of the force in member DG. That's 275 pounds. That is not the answer, though. That's not the force in GD. That's only the Y component of the force in GD. All right? So now that we have the Y component of the force in DG, then we can use, remember I told you the geometry of the truss is given. So just use a similar triangle situation. DGY over DG is equal to 3 over 5. 3 and 5, it's a 3, 4, 5 triangle. It was given to us at the first slide that talked about this slide, or this truss. All right? So solve the force in member DG, comes out to be 458 pounds. All right? And whether it's tension or compression, well, guys, look, we assume DGY to be pulling away from the joint D. All right? And it came out to be positive, 458 positive. So since it came out to be positive, that says the initial assumption was indeed correct. So it is in tension. Helen, I'm not sure. The summation about the point support F would indeed be equal to 0. I'm not sure exactly what you're asking me. But let me, guys, I want to talk to you about a few things here that are very, very important. On the test, if this problem was indeed on the test, the answer more than likely would not have been 458 pounds. All right? It would have been probably 460. The way the answers are, on the exam, they round the numbers up. All right. So, for example, if the answer comes out to be 458, they will give you 460, and they would say, uh, so more than likely, it's going to be, they will give you 460, but they will say it's closest to. All right? So they will say the answer is closest to 460. So they won't give you 458. And that's for rounding purposes. There's one other thing that I want to tell you. This is very, very important. I'm going to tell you now, but this applies to every topic, every problem that we will tell you from here on. Ryan is saying that on the test they say most nearly 460. Yeah, thank you. Um, this is what's going to happen, guys. Each problem, no matter what topic, they're giving you 4 answers. Out of the 4, 1 is correct, and the other 3 obviously are not correct. But those other 3, they don't just pull those other 3 wrong answers out of a hat. Those 3 wrong answers, in fact, they call them distractors. And I used to design problems for the exam, but I don't anymore. However, uh, when anybody submits a question for the PE exam, on the first top sheet, you show the example and describe the problem, and then the second sheet, you show very clearly the steps in solving the problem to get the correct answer. And then there are 3 other sheets that I have to attach, and each one I'm showing exactly what I did to come up with those each of those wrong 3 answers. And this is really important for you to understand that those 3 answers, they come up with those wrong ones by following commonly made mistakes. They project and they decide what is a way that most people would make a mistake here, and then definitely one of those would be a distractor, and it would be one of the 3 wrong answers. And I mentioned that here because, guys, pay attention. If you solve this problem the way I presented it to you, and then you came up with DGY, the Y component of DG to be 275, you come up with that number, you get excited, you look at the 4 choices, the first one is 275. You get really excited because you got a match. You got a match, but it's wrong. Do you see what I'm saying? So they want to make sure that you recognize this is the Y component, then you have to follow this other step in order to find the force in DG. So watch for those distractors. All the sessions that I cover, I will show you. I will definitely show you the possible ways, common ways that the people who design the problems, they come up with distractors. All right. One very popular way is units, not making a conversion, proper conversion. All right. That's a very popular way to come up with these distractors. What I want you to do is, please, when you study on your own, try to ask yourself, if you were designing this problem, how would you come up with distractors? All right, and if you do that, if you make that part of your study, then you will look for them, and you will be able to successfully identify them. All right, this is very, very important point. All right, next I'm going to cover shear and moment diagrams. Explicitly, shear and moment diagrams are indeed listed on the NCEES topics that will be on the test. So Remember shear and moment diagrams, it's basically a process where you have to draw the entire shear diagram or the entire moment diagram. However, please remember the exam is multiple choice. All right, so they cannot give you a beam like this and ask you to please draw the shear diagram or the moment diagram. They will give you this, but they will ask you specific questions about the shear diagram or the moment diagram. And for you to be able to answer those questions, you must be able to draw a complete shear and moment diagram and understand what it represents. For that reason, I'm going to walk through creating a shear diagram and a moment diagram using a load diagram such as this one. All right, so this is called a load diagram because the beam is given, the supports are given to you. One support is at B, another at E, and then the entire loading is given to you for the beam. All right, from A to C, we have this 20 kilonewton meter. Kilonewton per meter, 20 kilonewton per meter. Distributed load, rectangular load. There is a concentrated load of 60 kilonewton here at C, and then there is a free moment. This is a concentrated moment, a free moment at the point D. All right? So the first thing that we do is look for or solve for the reactions. There are two reactions, one at B. And I think the point B, and Helen, help me out. I switched to this slide. Now, slide 14, if you take a look at the point B, was that a pin? I think it's a pin. If you look at your handout, at the point B, if it was a pin, then there are two reactions. One at, Helen, thanks. She says at B was a pin, so there's a vertical force, and the other one at a pin, there's a horizontal, all right? I'm not showing it because the horizontal is 0 in this case, because when you look at it, there are no external loads in the horizontal direction. Therefore, even though that horizontal reaction actually acts at the pin, at the point B, but it's 0. That's why I didn't show it, all right? At E, however, it was a roller, so it's only a vertical FE. So the next thing that you need to do, and I need for you to please practice, make sure you know how to find these reactions, all right? And Fahmi asked that question earlier, but I don't want to spend too much time showing you how to find the reactions, but you must convince yourself. You don't need to prove it to me. Prove it to yourself that you can find these reactions and you could do it correctly. In this case, I'm showing you exactly how it's done. I'm writing the moment about the point B, set it equal to 0. I assumed clockwise, as you can see, positive. All right? And then I'm showing all the forces that would cause a moment about the point B. And the unknown is the reaction at E. It came out to be 40 kilonewton. Do me a favor. Don't need to do it right now, but make sure that you can do that and show to yourself that you could do that on your own, come up with that. And then once you have the reaction at E, assuming that's correct, then sum the forces in the Y direction and you find the reaction at the other support. All right? Now, once we have those reactions, then we can start drawing the shear diagram. Now here, for those of you, Helen, D is a pin. D is a pin. I'm sorry. D is this one you're talking about. D is neither. D is just a point on the beam. Yeah. Helen, thank you. That's an excellent question. Helen is asking, what is the point D? Is that a pin? That's a hinge? It's neither. D is simply a given point on the beam. The way we've shown it is because I wanted to show the exact point of application of that 120 kilonewton meter, that concentrated moment. Matthew is saying, how do you convert a distributed load into a single point load? Okay, let's take a look at this while we are looking at this slide. Look, just let's concentrate on this rectangular load. We have 20 kilonewton per meter. All right, it's a rectangular load. Think about it. It's 20 kilonewton per meter. So for every meter, it's 20 kilonewtons. How many meters is it acting on? 4 meters, all the way from A to C. So what's the total? The total load would be equal to the area under that rectangle. So 20 times 4, that's 80. That's a total of 80 kilonewtons. And where do we place? So that would be the single load. That would be the magnitude. And where do we place it? We place it right at the centroid of that rectangle. In this case, right in the middle. I hope that helps. If you have other questions, Matthew, send me an email. Okay, let's go. Let me get rid of this red. All right, guys. I need for you to help me go from a load diagram to a shear diagram. I'm going to give you a couple of, if I can write something here, I'll do it quickly. I want you to remember the relationship between the moment and the shear diagram. Moment is equal to the integral of shear with respect to dx. Okay? So in order to get the shear diagram, we have to integrate, in order to get the moment diagram, we need to integrate the shear diagram. All right? Now, what about shear? In order to get the shear diagram, we need to integrate the load diagram. All right, like this. Amgad, I see your question. Let me go through this, and then I can talk to you about your question. All right, thank you. So let's concentrate on the first one. Shear. To get the shear from the loading diagram, and remember the load diagram is this thing. I'll call it label W. All right, that's the load diagram. In order to get the shear diagram, which is down here, we need to integrate the load diagram. Now, I want to ask you a couple of questions, everybody. When we integrate something, when we integrate a function, what do we do to it? What happens to it? Think about, for example, x. When you have the function y equals x, integrating x, what's the answer? What comes out to be? When you integrate x, the answer is, okay, x squared over 2. Mina, is that Mina? Min says the answer is x squared over 2. Yeah, William Carpenter says if it's x squared over 2. Think about it. If it is x squared, what's the integration? It's x cubed over 3. Here's the bottom line. Whenever we integrate a function, we increase its order by 1. So if it's first degree, it becomes second degree. Second degree, integrating it becomes third degree. So remember that. Now, something else we do when we integrate a function. What is it? We calculate something when we integrate any function. Okay, Ian just answered it. Ian says we find the area under the function. All right, and Amanda is saying the same thing. Paul and Jonathan and Donald. All right. So when we integrate a function, two things we do. And this is very, very important, guys. I'm not just teaching you math. What I'm sharing with you, I'm going to apply to draw shear and moment diagrams. And if you follow this logic, drawing shear and moment diagrams, you will, I hope that you agree with me, it will be very simple. All right, here's what we're going to do. If, remember, when we integrate a function, we're increasing its order by 1, and we're finding the area under the curve. All right, very good. So if the load diagram between, let's say, A and this point, I'm highlighting it with red. All right, I want everybody to please participate in this. From A to where that reaction is, what degree curve is the load? In other words, this horizontal line. What's the degree of the horizontal line? Thank you. Thank you. Ian says 0. All right. Very good. Arash is saying 0. Okay. So here we go. If the W, the load, is 0 degree, the shear would be what degree? 1 degree higher. So we expect it to be a first degree curve. So the shear between A and B, we expect it to be a first degree curve. What does a first degree curve look like? Well, a first degree curve looks like a line like this. All right? That's a first degree curve. Now, let me show you. There are two ways of doing that. All right? The red one, or this would also, this green, or whatever that color is, that also, guys, that is also a first degree curve. So would the green be correct or the red? And how do we decide? Well, the red is correct, and the way we decide is because of the slope. All right? It's because of the slope. All right? How do we decide what the slope of this first degree curve should be from A to B? Well, we decide based on the direction of the load. Direction of the load. And in this case, the load is downward. So if the load is acting downward, the slope is negative. All right? So that's why the red segment is correct. All right. Tell me, what happens as we go from B to C? As we go from B to C, what is the degree? What degree curve does the shear need? Well, it would be a first degree with a negative slope. However, what happens at B is this 100 kilonewton reaction. Please make a note of it. At the point B, guys, there is a reaction of 100 kilonewton, which we saw by in the previous slide. All right? So the shear actually changes 100 units going up. So the net change is supposed to be 100. If we begin at negative 40, where do we end? 60, right there. Does everybody see how that's working? The effect of that 100 kilonewton reaction at the point B is that you are going to show, the shear diagram will show an abrupt net change of 100 kilonewton going up. So if you start from negative 40, it ends at plus 60. Now, help me out. Based on what I've just shared with you, what do you think the rest of the moment the shear diagram is going to look like from B to C? From B to C, go to the original load diagram. It's a 0 degree curve, so the shear needs to be 1 degree higher, so it's first degree. Positive slope or negative slope? Negative slope. Why? Because the loads are acting down. So let's take a look at next slide. There you go. Now, how did I end up at 20 here? How did I end up at 20? Well, remember I asked you what's the second thing that we do when we integrate something? Well, we find the area under the load, under the graph. All right. So if the value is 60, take a look. At the point B, shear is at positive 60. when we integrate the function from B to C, we are really integrating this 0-degree curve from B to C. All right? So when you integrate that function, that rectangular load only, we're finding the area under that load. What is the area under that load? To the right, you see it's 2 times minus 20. So the change, the area is minus 40. So pay attention here. If you start from plus 60 and the change, this area that's affected, is negative 40, so the net change will be 40 in the negative direction. So where do we end up? We end up at 20. All right, so that area is really the change between shear from B to C. So that's how we came up with that 20. Guys, how would you be tested on the test, on the exam for something like this? They could just give you the shear diagram for that segment only. And they give you, of course, 4 choices and say which one is correct. Do you get the hang of it? Now, what happens at the point C? At the point C, please pay attention. There is a concentrated load of 60 kilonewton. Now, because of the graph here, that's easy to miss. My recommendation is don't miss it. So the effect of that 60 kilonewton, it's a concentrated load at the point C. So the net change in shear would be 60 kilonewtons in the negative direction because it is acting in the negative direction. So if you start at positive 20, the change is 60 in the negative direction. Where do you end up? At negative 40. Now tell me, as we proceed from C to D, is there anything between C and D that would change the shear, which would really, in this case, it's the summation of forces in the y direction to the left of the cut. Is there anything that would change the summation of forces in the y direction from C to D? The answer is no, there isn't. Therefore, the shear remains constant at negative 40. Now, at the point D, we have this concentrated moment or a free moment acting on the beam. Please remember, if you have a concentrated moment like that, a free moment, it causes pure rotation and it has no effect whatsoever on the shear. Therefore, the shear stays negative 40 all the way from C to E, to that support E. And then, of course, at the point E, look at the original beam. It's a 40 kilonewton going up, so it brings you back from negative 40. It brings you back to 0, and this is what we expect, and we expect the shear diagram to close, so it comes back to 0. All right. Now, next thing I want you to do is to help me. This is the shear diagram, complete shear diagram, and the next thing I want you to do is help me draw the moment diagram. All right. Once again. And I hope that everybody is participating in this because it's important. And it's really not that difficult, all right? So from this, the left end, we're going to use the shear diagram to create the moment diagram. Now, remember, in order to get the moment from shear, what do we have to do to it? Integrate it, all right? So M is equal to the integral of V dx. All right. So ask yourself, what is the degree of the shear between A and B? What degree curve is that? You got it. It's a first degree curve. It was that line. All right. So a first degree curve, when you integrate it, it becomes a second degree curve. What does a second degree curve look like? Ryan, what's SFD? Is that a shear? I don't know what SFD is. All right, several of you are saying parabola. Yeah, second degree curve is indeed a parabola. So we would expect from A to B, we would expect from A to B, the moment diagram would be a second degree curve. What does, which is a parabola. What does a parabola look like? There it is. That's a parabola. That, guys, is a parabola. But I can also draw a parabola. I'm not going to try it because it's difficult to draw a parabola freehand. But it could also be a parabola with a on the top of the horizontal line. But this is the correct one because it has to have a negative slope. Now pay attention. The parabola that we have from A to B showing the moment needs to have a negative slope. It has a negative slope because the shear is negative between A and B. Please make a note of that. That's one thing that they will test you on the exam. All right. So from A to B, since the shear is below the x-axis, then the moment diagram needs to have a negative slope. What I'm showing here, this is indeed a parabola. It's a second degree curve with a second degree curve with a negative slope. All right. But on the test, they will ask you one other thing. All right. Yeah, Ryan and Alan, the shear force diagram will always have to close. If it doesn't, there is something that you've done wrong. All right. So here, look at that line. It's not very crisp, but that also, if you pay attention, that also is a parabola with a negative slope. And this is one that they do ask and try to see if you understand which is the correct one. Obviously, the first one is the correct one. And this is something that, let's go back. This is the correct one. But why? Why is this the correct and not the other one? Well, if you go to any reference book or let's say a strength of materials book or sometimes statics book, they actually show several pages of calculations and they prove to you which one is correct. But I will tell you the quickest way to do this. And I think Donald may have the idea. But yeah, Stephen also. But guys, this is what I will just give you a statement. I want you to write it down, and this will help you. The slope of the moment diagram, the slope of the moment diagram at any point is equal to the intensity of the shear at that same point. I'll repeat. The slope of the moment diagram at any point is equal to the intensity of the shear at that same point. All right? Now tell me, what is the intensity of the shear? Let me see if I can show this. What's the intensity of the shear at the point A? It's 0. I hope that you do agree that the intensity of the shear at the point A is 0. Then, based on the statement that I made, then the slope of the moment diagram at that point should be what? 0. All right? So tell me, between this parabola and the parabola below, which one has a 0 slope at the point A? The first one does. This one does. The other one has a slope other than 0. All right? So this is how you decide which end would have a 0 slope. See, with this one, guys, the parabola at the bottom, that's the one that has a 0 slope at the point B. And that's not what we anticipate. All right? So let's go back to this. This is the correct parabola. And then where do we get the minus 40? How do we know the moment is 40? Well, remember, when we integrate a function, we are finding the area under that function. Now, in this case, the change in moment. And please make sure you remember the word change. The change in moment is equal to the area under the shear diagram between 2 points. All right, so the change in moment between 2 points is equal to the area under the shear diagram between those 2 points. That's how I got the minus 40. Minus 40 kilonewton meter right there. Let's move on, guys. We need to move on. Okay, between B and C, what do you think the moment diagram is going to look like? Well, ask yourself, what is the degree of the shear diagram between B and C? It's a linear function like that. It's a first degree. All right. So the moment needs to be a second degree curve with a negative or positive slope. With positive slope. Why? Because the shear is above the x-axis. It's positive between B and C. Therefore, there it is. That's the second degree curve. It's a parabola with a positive slope. Now, the change in moment between this point and up here is going to be equal to the area under the shear diagram. Now, that area, you can convert it or divide it into a triangle and a rectangle. In fact, that's what I've done here. So that area is equal to 80 kilonewton meter. So 80 is the change in moment between B and C. So if you start from negative 40, the change is 80 in the positive direction. We end up at positive 40. That's where we got the 40. As you go from C to D, look, the shear is a 0 degree curve. Therefore, moment needs to be a first degree curve with a negative slope. Why negative slope? Because the shear is below the x-axis. Now, in this particular problem, this is very important because at the point D, what do we have? Look at the load diagram. At the point D, we have a concentrated moment equal to 120 kilonewton meter. That will introduce an abrupt change. It will introduce an abrupt change in moment at the point D. The question becomes, is that going to be an abrupt change in the positive direction or in the negative direction? In this case, and I'll tell you, there's only one way to decide, and that's going to be positive in this case. And here's what I'm going to tell you. Next time we meet on Thursday, when I cover mechanics of materials, I will have more to say about this subject. But for now, please remember, if you have a beam and you have a concentrated moment, like the one that we have here, somewhere intermediate to the supports. That means not at the support. It's not acting at the support, but somewhere between the supports. This is the rule. If that moment that is somewhere intermediate to the supports, if it is clockwise, treated as a positive moment. If it's counterclockwise, treated as a negative moment. In this case, it's clockwise. Therefore, its effect is going to be an abrupt change in the positive direction. So let's move on to the next slide. There it is. So the change is 120 kilonewton meter. You start from negative 40. Then that change in the positive direction is 120, so we end up at positive 80. Then as we go from D to E, it's a first degree curve with a negative slope because shear is negative, and that's what we get. All right, so this is the entire moment diagram. Let me ask you a question. They may give you this moment diagram and ask you, what is the maximum moment in this beam? So tell me, if I give you this moment diagram and I ask you, please tell me what is the maximum moment, what would you say? Okay, 80 kilonewton. Many of you, Arash, Paul, Brian, you are saying 80 kilonewton, And you're correct. No, Arash says 120. I don't know where you got that, Arash, but no, the answer is 80. It's 80. I think what he's doing, he's adding 80 and 40. But no, if this is the moment diagram, the designer will need to design this beam for such that it would resist 80 kilonewton meter. All right. Now, let me see if I can get rid of this. If I can erase this, it would be good. All right. Now, for the sake of discussion, everybody, don't change this, but for the sake of discussion, let's say that, and this is something that you might see on the test. Let's see, I give you a moment diagram, and instead of down here, instead of this being minus 40, for some reason, let's say it's minus 120 kilonewton meter. So the moment diagram now, Arash, take a look. If I give you this, and the moment diagram is like that. We have a negative 120 at B. Now I ask you, what's the maximum moment for this beam? Okay, Matthew says 120, 120. Min says 80. Okay, guys, the answer is 120. All right? The fact that it's minus 120, the negative only tells us how this moment causes the beam to flex, curvature up or curvature down. Once again, I will have a lot more to say about that during the Thursday session. But remember, and this is something common that they will ask you, it's a very simple concept, but remember, you need to look at the absolute values, and the highest value is, for example, in this case, the designer, she will need to design this beam such that it will be able to resist a moment of 120 kilonewton meter. All right? So please remember that. Let's move on. Okay. I have a series of problems here that are similar to what have shown up on some tests. In this case, the beam shown at the right is what? What do you think? By the way, this choice E, it's none, N-O-N, none of the above choices. And what would you pick here? Okay, Stephen says unstable. Several of you are saying unstable. You're correct. This is unstable, and I'll tell you why. It is unstable because this load P that you can see, it is acting at an angle. Therefore, that has a reaction in the X direction, also one in the Y direction. The supports are not providing any reaction in the X direction. Therefore, that is unstable. Okay, this is a good one. This is obviously a truss, and I need for you to help me. Help me solve this. And these are the sort of kinds of problems that you will see on the test because it's not very intensive in the calculations necessarily, but you need to understand the concepts to be able to answer it. All right? So what I need for you to, for example, help me, all of you guys, what's the force in member CE? Member CE is up here. This one, the top. All right, what's the force in member CE? How would you do that? By the way, if you have, before we do the solution, could you do me a favor? The word fixed, remove that. It's not fixed. That's a pin. At the point A, make that a pin support. At the point B, it's a roller support. All right? And this thing here, this is an L. This is a lowercase l. If I can write with that, this is supposed to be an L. But it really doesn't matter. That's an L. This is an L. You can call that Bob. It doesn't matter. AB and AE are equal. All right? So you can give it any dimensions you want as long as they're equal. That's what this problem is about. Now, help me out. Matthew says EC is 500 newtons. Well, okay, compression or tension. So CE, how would you solve it? Remember I told you about the T section? Well, here is not a T, but there are two members that are perpendicular to each other. What I would recommend, definitely, in order to solve for the member in CE, analyze the joint E. And those of you who are saying EC is equal to 500 newtons, you're absolutely correct. Khaled, you're with us. How are you, my friend? Khaled says 500 newtons. So here you're talking about 500 newtons, and for the summation of forces in the x direction at E to be 0, tell me, what do you expect? Would you, this internal force in EC, would it be pushing towards the E or pulling from E? You're correct. It has to push because those 500 newtons would have to um, cancel each other out. So absolutely, for summation of forces in the x direction at E to be equal to 0, the internal force in EC must be 500 newtons. The force would have to be pushing towards the joint, which makes it in compression. The answer, CE, is 500 newtons in compression. If you want to write down the equations, that's fine, but really by inspection, you should be able to tell. Next, I want you to please help me. What is the force in member AE? AE is the vertical member. What's the force in member AE? Okay. Matthew, Christopher, Jeremy, they're all, and several others are saying 0. You're correct. The member AE is a 0 member. And the one way you could see that, in fact, is by checking again the joint E and sum the forces. Let me see if I can look at the joint E and sum the forces in the vertical direction. There's nothing in the vertical direction to act along AE. So AE, the vertical member, is a 0 member. Let me ask you a couple of other ones, and then we'll move on. But what about BD? Who can tell me the force in member BD? This one. Note that BD is perpendicular to DC because they give you that angle to be 90 degrees. So what's the force in member BD? Who can tell me? All right. Jacqueline says 0, and indeed, BD, guys, is a 0 member. All right? It's not as easy seen, then we can see AE to be 0, but BD, that diagonal is a 0 member because, at D, there's nothing in that direction to act within it. Let me tell you something about 0 members. Vertical members are good. Vertical members are good candidates for being 0 members, but not all 0 members are verticals. Okay, as I showed you, BD is an inclined member and indeed is a 0 member. By the way, I'm going to move on, but the answer to all the members, I want you to solve all the members in this truss. This is very close to the kinds of trusses you might get on the test. So solve it, find the force in all the members. The answer, the results are on slide 63. Don't look at them now. Just look at those answers later on, all right? But the answer for all the forces is on slide 63. Okay, everybody tell me, what do you think about this one? The reaction at point A is what? Here's this is the point A. So what's the reaction at the point A? All right. Christopher says 0 at point A. You're correct. The answer at point A is 0 simply because, look, if you look at it carefully, this 100-pound force is directly placed at the point B. And you can, of course, write the moment equation also, but if you look at it very carefully, you will see this. All right? So let's move on. Okay. Those of you who are structural engineers, especially if you design steel structures, you're familiar with these books that I'm showing. We call it the Steel Design Manual. All right? Now, there are a couple of reasons why I'm showing these. On the NCEES guidelines, they also include the subject of deflection. They say deflection may also be on the test. Well, I will tell you, unless you're a structural engineer and unless you know quick methods of finding deflections, I think finding a deflection, it's not difficult, but the methods that we know, they take some time. They're long methods, all right, to find deflections. So if you get a deflection, there is some possibility you might get it, but not a high probability. But if you get on the test a question about deflection of a beam, what I need for you to do is refer to one of these books. Because these books, by the way, over the years, people have asked me, what are your suggestions, recommendations to take books to the exam? Which books would you recommend? Well, I will make some comments about that before this session is over. But I would recommend one of these books, Steel Design Manual. And these are, right now, those of you who are structural engineers, we are using the 13th edition, of this. But it doesn't really matter. For the morning exam, you can take any of these older editions, because when you look through one of these manuals, there are tables. By the way, there are tables that show shear moment diagrams for typical beams. If you get a match, one-to-one match, you could use that as a reference. There are also tables where they give you an equation for deflection along the beam. So here's what I'm showing you, why I'm showing this. If you get a beam problem and they ask you to find the deflection, please go to the tables that talk about the deflection and see if you get a match, one-to-one match between the loading and the kind of beam that they're giving you, and just use the direct equation to find that. All right? So you can go ahead and use this. That's one reason I have shown this book. And also, these are expensive, so I'm not suggesting you purchase one. Go ahead and get one from a friend, or if you have a library at your office, or secure one and take it to the exam. But now, Van is saying the 14th edition is out. That may be, but the ones that are used, the edition that's used, for example, in the afternoon structures is the 13th edition this next exam, all right? But here's what I will tell you. Many people ask me, what are your recommendations about books? And should we take a bunch of books or not enough books or not a lot? Here's my position on that. I think you should take as many books as you really feel comfortable and you want to take with you. However, this is a big caveat. I really want you to pay attention to what I'm telling you next. Every book that you take to the exam with you, you need to very clearly know exactly why you're taking it and what you will be able to find in that book and where in that book. All right? In other words, in any book that you take with you to the exam, you must review ahead of time and know exactly what you will be able to find in that book and and the reason why you're taking it, and also be able to quickly find whatever it is that you think you will find in the book. So I want you to avoid, for example, 1 day or 2 days before the exam, you're at the water cooler and a friend of yours, a colleague says, oh yeah, you're taking the exam. When I took it, I used such and such a book, and take it with you. And you not knowing anything about that particular book, you take it with you, and you may put yourself in a position to waste a lot of time trying to find things in this book that you're not familiar with at all. So the bottom line, and take as many books as you want, but please know exactly what you'll be able to find in each of those. Let's move on. By the way, these steel design manual, I think it's next week, I will cover a module, a session called structural design. When I cover that in the structural design session, I will walk you through one of these manuals, and I'll show you where you can find what within the textbook. All right? So we will do that. Now, this next slide I'm not going to cover. However, if you're a structural engineer and you intend to take the structural exam in the afternoon, I recommend that you follow this problem. The complete solution is provided, but those of you who are preparing only for the breath, and in the afternoon you'll take some other module other than structures, don't worry about that one. But do worry about this. All right, this is for everyone. This is a truss, and the next few slides show the solution for different members. What I would like for you to do is do this on your own. Try to solve this problem on your own and see if you can get the same answers that I have. Now here, this is an indeterminate structure. I told you at the very beginning of this presentation, you do not need to know how to analyze indeterminate structures for the morning portion of the exam. I have this in here for those of you who will be taking the structures exam in the afternoon. I'm not going to go over this, as I mentioned in the very beginning of this session, but I need for you to follow that. Now here, these are the answers to different members of that square truss on slide 33. I think this was the last slide, but we still have a few minutes. I want to talk about a few things. These are test-taking ideas. Mary Hill is asking a question: can books we take with us have notes in the margins or additions in the index? Absolutely. Yes, Mary. You can take a book and write as much as you want in the white parts of the various pages. Yeah, that would be fine. And by the way, you can take anything, even handwritten notes, with you on the test. The only thing is that it must be bound. All right? So whatever you take, as long as it's bound, and you can take it to Kinko's and have your notes bound, and it will be okay for you to use. The only thing they will not allow are loose sheets of papers in front of you. So make sure that you don't do that. Now, let me talk about a few things. It is really great to have you the next 12 or 13 weeks to review these sessions with you and the topics. However, you just showing up 4 hours a week and reviewing with us and listening to us is not going to be enough. Here's the rule, and I need your help with it. Each of you need to spend at least 10 hours a week, a minimum of 10 hours a week, studying these materials between now and the exam time. The 10 hours, you can spend 10 hours on a Saturday, or 5 hours on a Saturday, 5 hours on a Sunday, or you can spend 2 hours a night for 5 nights. However you do it, it's really up to you. But you do need to invest at least 10 hours a week preparing for the exam. And I do know that you will say, well, you're working full time. You may have small children at home. You have a family life. I accept that and I understand that. However, right now, this is a very, very crucial time in your professional and personal growth. And sacrifices must be made by you and those around you. So please make it possible for yourself to study at least 10 hours a week. And also, some of these sessions, depending on what your background is, for example, today, those of you who were structural engineers, I hope that you found this session today very, very boring and very elementary. It's supposed to be that way. But those of you who, for example, practiced transportation, geotechnical, and other fields of civil engineering other than structures, perhaps what I presented to you were not very familiar to you. However, let's say you specialize in water resources. When we cover hydrology and hydraulics, you will feel very comfortable there, and you will be bored, hopefully, when we cover that. So the idea is the morning session is a breadth exam, but once you look at each topic that's covered, it's really very fundamental. It's not very difficult. The difficulty is because when you specialize in a focused area, then you might have forgotten some fundamentals about the other disciplines within civil engineering. And that's what we work very hard to prepare you for the breadth exam in the morning. So it's definitely fundamental problems within each subdiscipline. My point is that I want all of you to please participate in the live sessions, or definitely study all the materials that we present to you, supplemented with a lot of problems, additional examples that you can find definitely in the print in the material that we will give you. Every session has some problems that we don't solve, and we leave it to you to complete. So at the very minimum, please do that. But what I want you to do is identify and recognize the topics that we cover within each subdiscipline and concentrate on those. A lot of people have this book, the comprehensive book. It's Ginsberg, I think. I think there is a thick book that a lot of people use to prepare for the exam. I think it's Ginsberg, but anyway, Lindbergh. Jonathan says Lindbergh. Yes, that's the one. That's a very good book, and I also have a copy of that. But I will tell you, the one problem with that book is that it's too comprehensive. It's not only very comprehensive, but it is too comprehensive. It covers everything there is about everything in civil engineering. So definitely, I think that's a very valuable book for you to have. But the value of these sessions, this course that you are taking part in, the value is that we will tell you what topics within each discipline, subdiscipline, we feel has the highest probability to show up on the test. So just concentrate on what we cover, those topics, and then go to Lindbergh's book and find more problems and examples that relate to what we cover. All right? And do as many problems as you can, and do it on your own, and make sure you learn the quickest way. And also train yourself to come up with distractors And as I said, as we go through the sessions, I will present to you different ways that they come up with distractors. I see Adam. Adam has a question. What counts as bound? Well, certainly, I think these days, three-ring binder also is acceptable. Three-ring binders, as long as you don't, the papers don't become loose, it's fine. A spiral binding would definitely be even better, all right? And easily you can do that. Let's see. Do you have any other questions? All right. At this point, I would like to stop. It's been great working with you this afternoon. I'll be here with you again next Thursday. Study hard, good luck, and I'll talk to you soon.